Okay, sorry about the delay. Chapter, I didn't put a title up here, but this is Chapter 3, Section 1. Increasing and decreasing functions. So first of all, here's what I'm going to try to accomplish today. We are going to learn a test for whether our function is increasing or decreasing at any time. I shouldn't say learn it. You already know it. We talked about it briefly last time. Secondly, we're going to find the critical numbers of a function, and I'm going to tell you, first of all, what those are and how to find them and how they will help kind of develop a little roadmap for when the function is increasing and decreasing. And then number 3, we'll try to be able to use increasing and decreasing functions to model some problems and solve them. Okay, now this looks awfully formal. I'm going to show it to you and then I'm going to put it in my own words. A function is increasing when, that's a fancy way of saying, as you move to the right on the graph, it goes up. That's really all that's saying. And a decreasing function is, as you move to the right, it goes down. I mean, if you look at this, this is just saying if your new point is bigger than your old point, that means you're moving to the right. And the second y-coordinate is bigger than the first coordinate, that means it's higher. So, simply put, the graph is going uphill from left to right. And the graph is going downhill when we're decreasing. So, sometimes, to be precise, by the time you're done with the definition, you're like, huh? It's really as simple as uphill, downhill. And for the tests, we're going to use something you already know how to do, and that is we're going to use f prime of x, the derivative, because the derivative tells you the slope of a graph at any place. Now, here's the deal. First of all, in order to do this, you got to be able to take the derivative, and as you know, there are a few places where you can't take a derivative, where we say a function is non-differentiable. First of all, the function has to be defined. You can't have, like, y equals 1 over x. You can't have this graph that never gets to a certain place. You can't take a derivative where there's a width, where we say it's undefined. So it's got to be defined. And secondly, you can't have remember, you can't differentiate at a cusp. So that's impossible. So if you had like this graph, absolute value, that graph is not differentiable where those two meet, because there's a, what? I mean, if I drew it correctly, there's a sharp point there. There is no slope at the bottom of that thing. So if it's differentiable on some interval from a to b, and if the first derivative is always positive, well, guess what? That means the graph is increasing on that entire interval. Okay, quick example. Let me just throw this out. So we have a graph, and let's say this is A, and this is B. So on the interval from A to B, I think you will agree that at every single place between those two, as we move from left to right, at every single place, you can just see, even though right here it gets close to horizontal, it's not. You can see that the slope's always going to be positive. So we would say that this graph, if this is f of x, we would say because f prime of x is always greater than 0 on the interval from A to B, then f of x is increasing on that interval. We always got to speak of an interval because later on the thing could take a dive down, but at least in that gap it's always going up, so we would call that increasing. So that's what this is talking about. And what if all the way from A to B it was negative every time? Well, then that's decreasing on that interval. And what if the derivative was 0 for every, that would be a graph that would look like this. Let me get a different color here. So if our graph, I don't know, did something like this, and here's A, and here's B, on the interval from A to B, as you can tell, the first derivative would always be 0, and that's called constant. So either it's going uphill and it's increasing, it's going downhill and it's decreasing, or it's 0 and it's constant. So just that's what these three. So there's only like 3 possibilities. Now, could it do more than that? Yeah. If I went from A to B, I could have it be increasing for a while and then decrease, But if we take a small enough interval, we can get it down to one of these 3 things. Okay. So guess what we're going to have to do in this lesson? We're going to be taking first derivatives, and then we're going to be analyzing, hey, is that thing positive, negative, or 0? Also, we want to identify critical numbers, so let's get it out. What's a critical number? Okay, here we are. First of all, the function has to be defined. There can't be a gap or an asymptote. Secondly, here are the 2 possibilities. If the derivative is equal to 0, so here's case 1, or if it's undefined. Like at an asymptote, where it just doesn't exist. Then we call it a critical number. So, one of the very first things we're going to do in a problem is we're going to take a function, we're going to find out, hey, are there any asymptotes in here? Any places where the first derivative is undefined or cusps? And secondly, are there any places where the first derivative is 0? Now, how are we going to find out when the first derivative is 0? Answer, we're going to find the first derivative, set it equal to 0, and find out when it happens. Okay, so I suppose it's time to look at an example. Here's one that's in the book. It's example 3 from the book. X cubed minus 3x squared. Well, first let's find the derivative. Really easy derivative, especially after some of the more complicated derivatives we've been doing. It's just what? 3x squared minus 3x. Does everybody see that? Because, let me know. Yeah, I know, you don't want to admit it. I shouldn't ask a question like that because nobody in his right mind is going to say, yeah, I don't get it. Sorry, but I'm trying to help, honest. But anyway, after you found your derivative, set it equal to 0. So just literally take 3x squared minus 3x, set it equal to 0, and then what values of x will make this come true? Well, now you got to use your algebra skills. You factor it. And the reason why is that? When you're trying to solve an equation equal to 0, you really have to, if it's quadratic, you have no choice but that, or if it's second degree or above, you have to get it factored. Otherwise, you can't solve it. So this one's factorable. 3 times x minus 1. And when is 3 equal to 0? Answer, never. Because last we checked, 3 was equal to 3. Okay, so that's out. When is x equal to 0? That's easy, when it's 0. And when is x minus 1 equal to 0? When x is 1. So, here are the 2 places on our graph where the derivative could be equal to 0. Now, what does that tell us? Well, first of all, it tells us that these are critical values, critical numbers. Okay. And it tells me that at that, when x is 0, there must be a horizontal tangent line that has a slope of 0. Okay, so that's why is that a big deal? If we want to know when a graph is going up or down, then isn't it nice to know when it's 0? Because they're going to be kind of like the dividing lines. Okay? All right, then what we're going to do is check on either side of those. So we set up kind of a little chart. Yeah, they do that at the bottom. I'm going to scroll down here. So do you see how, all right, we've got all the points to the left of 0. That's what this is. Then we got all the points between 0 and 1. And then we got all the points to the right of 1. See, what we've got going here, hopefully you can spot this, is that, I mean, here's 0, and here's 1. They're right on these dividing lines. Those are the two critical numbers. All right, so we want everything to the left of the first dividing line, and we want everything between the two, and then we want everything to the right. So do you see why we came up with 3 columns? All right, well now, let's just take any value to the left of 0. Now they just happen to pick -1. You could have picked -6 trillion if you want. Just anything left of 0. Well, you probably want to pick a small number because it's easier to calculate with, and 1 is really easy to calculate with. Here's your derivative right here. What's f prime at 1? Wouldn't it be, let's see. What am I doing wrong? Oh, I'm sorry. We have to pick -1. What's f prime at -1? That would be 3 plus 3 or 6. Okay. So obviously is 6, now here's a really rough one. Is 6 positive or negative? It's positive. Therefore, in this interval, we know the graph is going uphill. Okay. Now, pick a representative point between 0 and 1. They did probably what I did. They picked 1/2. What's f prime at 1/2? Okay, let's be careful here. 1/2 squared is 1/4. 3 times 1/4 is 3/4. Minus 3 times 1/2. So what is that? 3/4 minus 6/4, which is a -3/4. And it's negative. Therefore, in this interval, the graph is decreasing. And now, pick any old point greater than 1. They picked 2. What's f prime at 2? 12 minus 6, which is 6. 6 is positive. Therefore, so now, let me just show you what's happening here. On a grid, here's what we just found out. Now, please, just take this as a generic observation, okay? I don't know where the graph is, but I do know this. What were the 2 critical points? I'm just going to mark those with dots. And what did I know? What did I say is true when the graph is to the left of -1? It's increasing. So it's probably, doing something like, we don't know what it looks like, but it's going uphill. Then it gets to 0. And what is it doing between the two? It's decreasing. We don't know where, but when it gets to this point, we don't know where that is, so I shouldn't have put the dot there, but when it gets to 1, after 1 it's increasing, right? Now this is just a generic graph. I have no idea how high it is or what shape it is, but do you see how we've learned this? We've learned that to the left of 0 the graph is going uphill, then it's momentarily at 0, then it's going downhill, and then it reaches a critical point down here, and then it increases. That's what this increasing, decreasing stuff tells you. Now, again, I don't know that's where the graph is. How could I find out? I could find the values and nail it down, but I'm just trying to show you the little mind movie that should be rolling in your head. Oh yeah, it's increasing. Yeah, then between the points it's going downhill. And then after that, it's going uphill. And in your mind, you're kind of thinking like that. Okay. Now I got to find my way back. Okay. So I guess it's time now. Let's pick another example from the textbook. Let's take number 15, which is on page 180. Am I in the right place? Yeah. So number 15, page 180. Strange color. Okay. Now the equation is y equals x cubed minus 6x squared. And you notice in the directions it says, find the critical numbers and the open intervals on which the function is increasing or decreasing. And then lastly, let's go all the way and let's sketch the graph. Okay. Critical values. Step 1, find derivative. I'm going to just call this f of x. So you're trying to find f prime of x. Nice, easy derivative. Okay, set derivative equal to 0. Solve for x. So this could equal 0. Of course, the only time that will happen is when x is 0. And of course, this could equal 0, and that will happen when x is 4. So these are the critical numbers for this graph. What does that mean again? It means either this thing is off the map, we don't have any asymptotes on this one, or we have a horizontal tangent. All right. Now, set up your intervals. So 0 is a key number, 4 is a key number. So what we're going to do is set up some columns here. So what about, like in column 1, we want to know when x is less than 0. Well, should we take like -1? What's the derivative at -1? When you plug in a -1 here, what do you get? 3 plus 12, which is 15. So obviously it's positive. We don't really care about the number. All we care about is the sign. Therefore, wouldn't you agree that on this interval from -infinity to 0, our function is increasing? Does everybody follow that? I'm seeing some funny looks. Let me know what you're thinking. Let me take the second interval. All right, how about between 0 and 4? Pick a number between 0 and 4. Anybody? 2 it is. Okay, we could have picked any number in there. What's f prime at 2? Well, plug in 2 is 4 times 3 is 12. 12 minus 24 is, that's a negative, correct? So that tells us that in that interval, the function is decreasing. And then pick a number greater than 4. I'll be real original and say 5. Okay, what's f prime at 5? Well, it's going to be big. What do we have? 25 times 3 is 75. 75 minus 60 is 15. It's positive. So what did you just find out? We know that the function is increasing on negative infinity to 0. Notice I use rounded parentheses. Why? Why didn't I use like square brackets for the interval? Because I don't want to include the endpoints. Because if I include 0, we already know that's no way that's positive. At 0, we already know it's 0. So I got to go just up to it. That's why I used the rounded. That was not supposed to happen. It's also increasing on four comma infinity, and it's decreasing on the interval from, those are in no particular order. If you're wondering why did I put I could have done those in order and said increasing, decreasing, increasing. I decided let's bunch all the increasings together. It does not matter. Let me know. Anybody have a question on what I just did? We're going to do the last step, but I wanted to give everyone a chance to get into that a little bit. Now we're supposed to make a graph out of this. Okay? So, yeah, probably my units are going to be goofed up. Maybe I should copy. I got to remember it's x cubed minus 6x squared. Okay, we already know critical points are at 0. I'm sorry. Yeah, at 0 and at 4. Okay, what's the y-coordinate when x is 0? Just plug it in. Sorry, there should be an equal sign there. Just plug it into the function, and you get a 0, right? So we know that point's on the graph. And the other critical point is 4. What's the y-coordinate when x is 4? Let's see, 4 cubed is what, 64? 64 minus 96. Is that right? 16 times 6 is 96, isn't it? So 64 minus 96, I've got negative 32. So at 1, 2, 3, 4, negative 32. Whoa, how am I going to do this? Let's have each line stand for 4. Okay, now, sorry, I'm having a little problem with dimension, but now, basically, what they want you to sketch is, all right, remember we said it was increasing to the left of this point? So now you're just going to make something that's coming uphill here. We don't really care what it looks like. And then it should level off and get horizontal right at the critical point. Then it's supposed to decrease from here to here. So we're going to have this thing do something like this. And it's got to level off when it gets to the point again. And then after that, it's supposed to increase. Now, you're probably thinking, well, that's not a very precise graph. You're right. But that's all they really want you to do at that point. Now, what if we wanted more exact points? Well, we can do other things, and we will be doing more later. So, is it important to know when a function is increasing and decreasing? It's incredibly important. It's so important they put up a whole section here for us to do. Questions on a problem of that type? Should we see what it really looks like? The only problem is my units are so goofed up. I've got this thing incredibly squished vertically. But let's just call up this graph and take a look at it. X cubed minus 6x squared. And you can just see enough there. You can see how it comes from below. It does level off at 0. Then it goes down, just like we said, and it goes down to that point at negative 32 where we were. And then it comes back up and kind of just keeps going on forever, and so we've kind of confirmed it. I noticed when you go to the only difference between the directions on 9 through 18 and 19 through 28 is on 9 through 18, they just want you to sketch the graph like I did in red. And then in 19 through 28, they want you to take out some graphic calculator or some technology and sketch the graph that way. So I've kind of shown you one of each there. So let's move on to another one. Why don't we go to that 29 through 34 section. 29 to 34, find the critical numbers in the open intervals on which the function's increasing or decreasing. Okay? Notice it says hint. Check for discontinuities. And then when you're done with all of that, sketch the graph. Check for discontinuities. So it's like saying, hey, don't forget to check for discontinuities. And guess what? When they tell you to do that, there's going to be some. Okay, what's a discontinuity for number 29? Can you see it right away? Yeah, and why is that? What's wrong with 4? 0 in the denominator, right. So, and what else could x, let me just write that down. X cannot equal 4. What else could x not equal? That's right. So guess what? Those are discontinuities. Okay? So in other words, can I take a derivative at x equals 4 of this thing? Answer, no. Because the graph literally has an asymptote there, and there's no graph. How can you find the slope of a graph that's not there? You can't. So these are critical numbers. Now let's go on and take a look at the function some more. We have 2x over 16 minus x squared. Well, we have to take the derivative, don't we? Okay, what do you want me to do? We have a choice. We can do the quotient rule, or we can write 16 minus x squared as 16 minus x squared to the negative 1 power, and then do the product rule. Somebody just make a choice. Product rule. So you want me to think of it like this. Don't want to touch that crazy quotient rule, huh? By the way, is there a shorter way of writing 16 minus x squared to the minus 1? Can I like just make that 16 minus x to the minus 2? No, because doesn't the minus 1 also affect the 16? Yeah, there's no shortcut. Okay, so here we go, product rule. The first times the derivative of the second I guess I'll close parentheses here. Okay. Plus the second times the derivative of the first. Okay. Uh, let's see. Let's simplify this a little bit. We've got 2x on top. Actually, what's 2x? First of all, we have a negative times a negative. Can everybody see this whole thing's going to be positive? That's, because that doesn't affect it. We got a negative times a negative, which is a positive. So we're going to have a positive. And then we have 2x times 2x, so that's 4x squared. Now we've got this thing on the bottom and squared. Okay, and then plus, and we've got this on the top and that on the bottom. Now, you know what? I'm not even going to bother with getting a common denominator. You got it. Maybe I'm taking too loose of an approach here, but on the test you would have been asked to bring that together. Actually, yeah, maybe we better. I apologize. I just realized that in the next step it really would be nice to have it simplified. So, how can I get these two so I can bring them together? Well, I need a common denominator. And how could I achieve that? Couldn't I just multiply this by 16 minus x squared? Now I'd have two of them, just like over here. Of course, if I do it on the bottom, I got to do it on the top. Okay, what do I get? I've got my common denominator. And on top, I get what? This is 32 minus 2x squared. So 4x squared minus 2x squared is 2x squared. And plus 32. Okay, there's my derivative. Okay, now, what's the next step? Set the derivative equal to 0. How can I simplify this really easily in the next step? If I want to solve for x, couldn't I just multiply both sides of the equation by 16 minus x squared, that denominator? And then it's goodbye denominator, right? So now I just get 0 equals 2x squared plus 32. Oh, that's not very hard to solve. Factor out a 2. No, let's not factor it out. Let's subtract 32. Let's divide both sides by 2. And let's take the square root. Okay, this is going to be an imaginary, isn't it? Hand up. Yeah, go ahead. Okay. Good question. I took both. Now that we have an equation here, I decided to multiply both sides by 16 minus x squared squared. So what happens on the right is it cancels, and on the left it just, and that's how that whole denominator just went bye-bye. Okay. Well, the only problem is we came up with an imaginary number. So, had this been a normal square root, we would have found some additional critical numbers. Now I want to remind you, we already found, remember right off the bat, you guys found these two critical numbers. What we were doing in this process is trying to find if the first derivative equals 0 at any time. But you know what? We never found one, did we? So, okay, so we're down to just these two critical numbers. Okay, it's now time to set up our chart and our intervals. So we'll just do a new page for this. So what were they? 4 and negative 4. Okay, So pick a number to the left of negative, to the less than negative 4. How about negative 5? Where's our derivative? It's this guy right here. Here's our derivative. Let me copy that and bring it down. I'll bring it to the new page. So just a reminder, there's our derivative. Now, I was setting up our chart. When x is negative 5, what's f prime at negative 5? Yeah, what's f prime at negative 5? Well, let's find out. What's negative 5 squared? 25. 25 times 2 is 50. 50 plus 32. So that's a positive. And on the bottom, what's 16 minus negative 5? Negative 5 squared is 25. 16 minus 25 is negative 9. Negative 9 squared is 81. So it's a positive over a positive. So it's a positive. See, the cool thing about this arithmetic is you don't really even care about the number. And because it's positive, this thing must be increasing on that interval. How about somewhere between negative 4 and 4? What's the super easiest number to pick between negative 4 and 4? You bet. X is 0. What's f prime at 0? Well, let's see. 0 plus, so we get 32 on the top. We get a positive on the bottom. Positive over positive is positive. And how about after 4? 5. What's f prime at positive 5? Same thing, isn't it? So, looks to me like this is forever increasing, but you got to remember that, I forgot to write this down. It's supposed to be positive. If you're wondering, how can it forever increase? Well, it can, but the thing is, don't forget, what do we have at negative 4 and 4? Yeah, and what does a discontinuity mean on a graph? What kinds of graphs disappear? Graphs that have asymptotes. Sometimes they have holes, but the most common disappearance act is the asymptote. So what we got going on is the thing is going uphill, then it disappears. So it's kind of like there might be an asymptote here. Okay, then it's going uphill, and it disappears again. Another asymptote, and then it's going uphill again. So we've got a couple asymptotes in between. We should probably nail down a couple points too. What's the point when x is, I don't have the original function here. You got it in your book. Tell me some points here. What are the coordinates at, what's y when x is negative 5? Could somebody quick do that? You get negative 10 on the top. Negative 9 on the bottom is 10/9. Does that sound right? Would somebody quickly check that for me? I'm trying to do a little too much here. Let's see, on top. I'm doing 29, right? So negative 5, you get a negative 10 on the top. Yeah. Okay, and let's do this one. What's the point for 0? You get 0 on it's 0. Okay, cool. So that's at the origin. And what's the point for 5? Now you get a positive 10 on the top. You still get a negative 9 on the bottom, so you get a negative 10/9. Okay, so now based on this analysis we did, and we know we're going to have some asymptotes, at 4 and negative 4, let's try making a sketch of this. Again, I'm going to do it scrunched so that I can get it all on the same screen. What I'm going to do is get rid of this guy. Okay, so we've got, let's put some asymptotes in at 4 and negative 4. Okay, then let's put our points in that we do know. We know there's a point at negative 5, negative 5, negative 1 and 1/9. No, negative 5, positive 1 and 1/9. Sorry. Get rid of that. We know we have a point at 0, 0. And we know we have a point at 5, negative 10/9. And supposedly it's increasing in all places. So how could that be? It could go like this. I mean, we don't know exactly what this is shaped like, but... And I could use some more points, but... It could be looking like that, okay? And therefore it is consistent that you could have increasing in all locations. Now that's pretty sloppy, but that's the idea. So let's check that on the graph software. Okay. Let's undo that one. Let's put in a new function, which is 2x divided by 16 minus x squared. I love that you don't have to put an asterisk in when you want to tell it multiplication. Yeah, except that I kind of drew in the wrong places. Do you see how, number one, we've got two asymptotes. We got the S-shaped curve right in the beginning, but without picking more points, I dipped too low to the left, and I went too high on the right. By the way, is this... I know you can't see this. Let me zoom in here a little bit more. I want to ask you a key question here. First of all, is this consistent? Is this graph really increasing everywhere? Yes. So that makes sense. Is it even increasing here? Yes, slightly, but it's still increasing, and it's going to keep getting higher and keep getting closer to 0, but never quite gets there. Okay. So what we could have benefited from is some of our old algebra. Remember how we found asymptotes? I didn't do any of that because I wanted to focus in on the increasing, decreasing. Okay. So let's see. Quickly recap here. When a function is increasing, its derivative has to be positive. When a function is decreasing, its derivative has to be negative. Because you can't take a derivative everywhere, the points where you can't take a derivative are called critical points. And what other points are critical points? When the first derivative turns out to be 0. So notice several times today we found the first derivative and then we set it equal to 0 to solve it, to find the other critical points. Once you got all your critical points, set up a table with your critical points as dividing lines. Pick a representative point somewhere in the middle of the interval. Go ahead and calculate the sign of the derivative. If it's positive, it tells you the function is increasing. If it's negative, it tells you the function is decreasing. That's basically the idea of the entire thing. Did anybody look ahead at the assignment? I'll go take a look. Okay, it's every other odd. 1, 5, 9, the last one being 27. So I gave you a shorter list because there's kind of a lot to do on each one. 1, 5, 9, dot, 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 27. Everybody get what that means? Thanks.